Good afternoon, students. Let us start the class. We were discussing this phase shift oscillator in the previous class, and we have been seeing the circuit implementation using operational amplifier. As operational amplifier is an ideal amplifier, its input impedance can be considered as infinity and its output impedance can be considered as 0. So in such a case, these three CR networks can be directly utilized for producing 180-degree phase shift. That means 60-degree each at a specific frequency. You already know the RC circuit's angular performance, leading and lagging performances of the passive component circuits. So that way, three RC circuits can be connected in series so that each will produce a 60-degree phase shift at a specific frequency, and that specific frequency will undergo 180-degree phase shift here, and that is going to be fed back to the amplifier. As you already know, the amplifier's internal noise itself is ranging from 0 till infinity, and all the other noises will not be amplified. Only a particular noise which is having the desired frequency which we want out of the oscillator, that particular frequency is going to undergo 180-degree phase shift because of the RC networks. The other frequencies will not get amplified at all, so they remain at their minimum amplitude inside the amplifier. Even afterwards, these noise frequencies will remain inside the transistor, but they will not be of a predominant amplitude because they have not got amplified as such. So that is how this phase shift oscillator is working. Let me proceed to the next slide, and I have already told you about the formula for this. F equals 1 over 2 pi RC root 6. Let me proceed to the next slide. Now within FET, how can we have phase shift oscillations? You can see that the FET circuit is almost same as the op-amp circuit itself, which means even FET is having a very high input impedance as there is no gate current. So it does not matter, even if we connect this R here, it does not matter that Zi, even if it comes in parallel with R, the value of R is much smaller compared to Zi. So we can directly have a amplifier connection using this FET, and then we can have a RC networks as the feedback. And the formula holds good in the same manner, 1 over 2 pi root 6 and RC. And we are using the fixed bias network for the FET. You can see that this R itself is connected to ground here. So which means this is like a self bias, sorry, not a fixed bias, it is like a self bias circuit because we have RS here. We have to be careful, if at all we have to use the voltage divider bias for phase shift oscillation. The reason is, if we have this voltage divider bias here, let us say we have this R1 and R2 here. Now that R2 is going to be coming in parallel with R. That is why you can see here that the FET amplifier used is of self bias configuration. Even a fixed bias configuration also can be used, but not voltage divider bias, because that R1 and R2, they are going to come in parallel with the actual R which is used here. That is the care which we have to take when we use FET as the phase shift oscillator. So in general, Ri is much larger for the FET. Further, impedance of the feedback network is also much larger when compared to RL. Even if we connect one load resistance at the output here, the impedance of the feedback network will be much larger here because of the series combination of capacitances. So that way, the oscillator will not have a loading effect when a load is connected to the output. That is the meaning here. Now, we have already performed the AC analysis for the FET circuits in the second module. You will have to recall that now. Here the gain of the circuit is A equals Gm into RL, where Gm is the transconductance. Now this RL can be this small RD we have here within the FET and capital RD we have here in the AC equivalent circuit. That capital RD is going to have a AC ground at VDD. So small RD parallel with capital RD itself is going to be the load resistance for this particular circuit now, because there is no other load connected here. So RL is the parallel combination of capital RD and small RD. That is why capital RD into small RD divided by capital RD plus small RD, that is load resistance. Why this gain has to be important? We have seen earlier that for the phase shift oscillator, the gain factor is also playing a critical role, because it is A into beta that is going to satisfy the Barkhausen criterion. That is why the amplifier's gain is discussed here. Now there is an exercise. Two kids are working with the exercise tools. But in our teaching learning process now, the exercise is basically a mental exercise along with pen and paper. So I'm going to give an exercise now. Try to solve this exercise on your own. An FET has Gm equals 5 millisiemens and small rd equals 50 kilo ohms. Obtain the value of C and capital RD for the phase shift oscillator's frequency of 10 kilohertz, choosing R equals 4.7 kilo ohms. My dear students, can you quickly work out this problem? I'll be waiting. You'll have to find out the value of C. Value of R is given and value of the frequency F is given. You already know the formula. F equals 1 over 2 pi RC root 6. Now in that R is known, F is known, you have to find out C. Tell me the value of C, that is enough. The remaining things later on, I will show you the answer. For the value of RD, I will show you the answer later on. You can quickly calculate the value of capacitance and tell me the answer. I'm waiting. Lokesh has given the answer 13.8 microfarad. Sayan has given the answer 1.3 nanofarad. Let us see. As far as Lokesh's answer is concerned, I don't think that is a valid answer, because microfarad is a very large value here. We will not be using microfarads. It will be nanofarads and picofarads. So is it 1.3 nanofarad? Let us see the answer. The answer is 1.38 nanofarad. Now Lokesh has to check his multiplier. He has come nearer to the answer. He has got 13.8, but somewhere you will have to substitute the multipliers carefully. See, 1 over 2 into pi into root 6, that root 6 is 2.45, and into R, that is 4.7 kilo ohms, into F. F comes to the denominator here because C goes to the left hand side numerator. So this 10 kilohertz is the frequency. So we substitute all that, we get capacitance is 1.38 nanofarad. Now to find out RD, we already know that the gain has to be greater than 29. So we will have to assume a gain now, because we have a formula for the gain. But small rd is given, capital RD is not given. Gain is also not given now. A is also not given. So what to do? We know that in the case of a phase shift oscillator, the gain of the amplifier must be greater than 29. So in that case, even in the tests or even in the exams, when such problems are given or such exercises are given, there can be multiple answers now. You have to assume a gain which is more than 29. Now you can assume a gain of 30 also, 35 also, 40 also, 45 also, 50 also. In any which way, you can assume the value for A. Once you assume the value for A, you know the formula for A already, right? I'll show you in the previous slide. See, there is this formula for A. A equals GM into RL, whereas RL is nothing but capital RD into small rd divided by capital RD plus small rd. Now this capital RD is given. Sorry, capital RD is not given. Small rd is given. And A is not given. We have to find out capital RD. We have to find out this capital RD. Gain of the circuit is not given, because the value of RS is also not given. Now, we will have to assume the value of gain. It must be above 29. So, you have a freedom now. You can assume any value of A which is greater than 29. So, there can be multiple answers. I will show you my answer now. As A has to be greater than or equal to 29, I am choosing A to be 40. When I choose A to be 40, I can calculate that RL 40 by 5 millisiemens. See, GM is 5 millisiemens. So RL, that load resistance, which is a parallel combination of drain resistance and the internal resistance, that is 40 by 5 millisiemens, that is 8 kilo ohms. Now, we will have to substitute that 8 kilo ohms in the parallel combination that was meant for this small rd and capital RD for the RL. So substituting that way, we get capital RD equals small rd into RL divided by small rd minus RL. We get an answer of about 9.52 kilo ohms. So the nearest standard value for the drain resistance is 10 kilo ohms. Now you can observe here, I have chosen A to be 40, because of which I am getting this answer. If you choose A to be 35, you will get a slightly different answer. You can choose A to be 50 also. You will get a slightly different answer, because these are basically designs which we decide. When there are two unknowns, then one unknown we have to assume in our own way, and we have to find out the other unknown. That is the method here in solving this exercise. Let me proceed now. Now, how to have a BJT phase shift oscillator? Even in BJT, you can go for fixed bias or self bias or emitter bias. But you already know that the voltage divider bias itself is the most stable biasing circuit with BJT. Now, we are using this voltage divider bias itself. Even if you use fixed bias and self bias also, it is not going to be of great advantage in the case of BJT, because in the case of BJT, input impedance is really very finite. We have already studied the RE model and the hybrid model. The input impedance of the BJT circuits will be a few kilo ohms. Unlike the FETs, in the case of FETs, the input impedance will be in the range of mega ohms and giga ohms. So now, when we use the BJT as the phase shift oscillator, amplifier for the phase shift oscillator, you can see that a C and R is given, a C and R is given, and then C, then this R dash is there. Now you can visualize this. Let me annotate now. Let me indicate an input impedance here. Let me change the color. We can indicate, we can visualize an input impedance here. Let me call it as Zi. This is the impedance of this whole circuit, impedance of the whole amplifier. Now you can see, if at all we connect one R here, if at all we connect one R here, assume this R dash is not there. If at all we connect one R here, now this R is going to be coming in parallel with Zi. When that R is going to be coming in parallel with Zi, what happens here is, you have chosen R to be 4.7 kilo ohms in that particular exercise. So this will be 4.7 kilo ohms. This also will be 4.7 kilo ohms. But when we connect this 4.7 kilo ohms here, now this Zi is in the range of, let us say, 2 kilo ohms. Now that 2 kilo ohms will come in parallel with this 4.7 kilo ohms, and then we have a problem. The last R will not be equal to the 4.7 kilo ohms because that is in parallel with the input impedance. Now the whole CR circuit will not produce completely 180 degree phase shift because there will be a deviation in the last R value. How to solve that now? For solving that, we will have to consider the input impedance of the BJT circuit now, which we did not do in the case of FET, in the case of op-amp, because there the input impedance was very high. Now in the case of BJT, the input impedance is not very high. So now what is this R dash basically? Can anybody tell me what will be the value of this R dash now? Can anybody tell me what will be the value of R dash now? No idea? Let me write it here. Now this R dash plus Zi should be equal to R. Right? See, this Zi is connected to ground. Now we should have a series resistance in such a way that R dash plus Zi should be equal to R. Now it is equivalent to one R getting connected to ground. I hope you got this point. But the problem here is we don't know the Zi value, right? The value of Zi will be changing because the value of Zi is dependent on the value of beta of the transistor. Beta will be changing from device to device. So what is the solution now? If at all you know in prior about the impedance of an amplifier, then you can choose a value R dash in such a way that let us say this Zi is 2K and let us say R what we want is 4.7K. R what we want is 4.7K, then you should have R dash as 2.7K. So 2.7K plus 2K becomes 4.7K. Now that is the value which we should choose for R dash so that the phase shift oscillator will work. Now, as we do not know in advance about the value of Zi, because we are not sure about this, we are not sure about this 2K. Beta will keep changing from transistor to transistor. So what is the best solution? The best solution is use this R dash as a potentiometer. That is what we do in the lab. When we conduct BJT phase shift oscillator in the lab, as the input impedance of the amplifier circuit is finite and we actually do not know the actual value of the input impedance, but we know the approximate range. It can be between 1 kilo ohms to around 3 kilo ohms, in between 1 to 3 kilo ohms. That is the approximate range. We have worked out many examples in the first module and we know about it. So in such a case, we can connect a potentiometer from 0 to 10 kilo ohms. Potentiometer is a variable resistance. So we can connect a potentiometer here and now you know that R dash is equal to Zi plus R. So in such a case, when you switch on the circuit, immediately the circuit will not work as an oscillator or may not work as an oscillator until you fine tune this potentiometer such that only when this R dash value reaches the value of what? R minus Zi. R dash is basically R minus Zi. So when that value of R dash reaches that, then we will have a total 180 degree phase shift across this network, and that is how oscillator starts working. So even in the lab, this potentiometer needs to be slightly fine tuned until you get the output. That is the remedy which we take in case of BJT phase shift oscillator. Okay, I hope you understood this point. Now this is the complication when we use BJTs, when we use them for oscillators. You can see a difference in the expression for the frequency also. You can see in case of earlier circuits it was 1 over 2 pi RC root 6 only. But here you can see 1 over 2 pi RC root 6 is also there, but inside the square root you can see 6 plus 4 into RC by R. Now why this RC is coming into picture? Again you can see the output impedance is also non-ideal. Here RC and R are working like a voltage divider network for the output signal itself. Of course, it was there even in the case of FET. But in the case of FET, the output impedance was actually lesser. But in the case of BJT, output impedance is slightly larger. So when we consider the complete frequency domain analysis of this circuit, formula slightly changes. That is the reason in the case of BJT, you will have to remember specifically the value for frequency is different. You will have to remember additional term 1 over 2 pi RC root 6 for general op-amp or FET phase shift oscillators. But if it is with BJT, then you will have to remember this formula 1 over 2 pi RC root 6 plus 4 into RC by R. Okay. Here Ri is much lesser, hence one solution is to use an emitter follower at the input stage and the other solution is to use an additional resistor R dash in series with Ri such that R dash plus Ri is equal to R. This I have explained you already. Instead of Zi, here I have mentioned Ri, input resistance. If you don't want to use this R dash, then the other solution is to connect the R as it is here, having 3 RC networks here, then to connect to an emitter follower, because the emitter follower is going to have a unity gain. So emitter follower can be used for impedance matching that way. Emitter follower will have very high input impedance. So let me show you that way. What can be done in such a case is, this can be shorted and you can have the regular R here. You can have a regular R. But here there must be one more amplifier. There must be this emitter follower or a common collector amplifier. Now when there is a common collector amplifier, this is having a gain of unity and there is no phase shift also. You already know that emitter follower circuit will not introduce any phase shift and it will not introduce any voltage gain. It is having only a current gain. That means input impedance of this emitter follower is very high, output impedance is very low. That way, when the input impedance is very high, this R itself will suffice our purpose. Let me remove this, let me change the color and let me short it now. So we can short this R dash and now we can have an emitter follower. But the additional complication is we need another BJT and another biasing circuit for emitter follower. So that is inclusion of additional components. That is one solution. The easier solution is to use in this way, in whatever way in the picture it is shown. This is the easier solution. Now here, as this particular BJT is going to have a HFE or beta, when we perform a frequency domain analysis of this particular circuitry, we have one more requirement now. That is, the beta or the HFE of the transistor must be greater than this particular factor. You don't have to worry about how we obtain this factor. As I have told you, we don't have the derivations of this formula in our syllabus because they are much more bigger work or slightly more complicated work. Scientists have already done it and we are only using the formulae. So in that case, HFE has to be greater than 23 plus 29 into R by RC plus 4 into RC by R. This may seem to be a crazy requirement, but if this requirement is not met, then the circuit will not work like phase shift oscillator. That problem is there. That is why even in the formula you will see that square root of 6 plus 4 into RC by R. So the beta of the transistor must be larger than this particular factor which is shown at the right side. Okay, let me proceed. What you see is called as a breadboard. In the breadboard, you will see this LM741, which is a very popular operational amplifier. And you will see a sine wave output here. And you can see some resistors and capacitors connected along with the potentiometer connected. You can see this is a small potentiometer. We also call it as preset. By using a screwdriver, you can slightly rotate it so as to have a variation in the resistance. Actually, its resistance is a complete circular or semicircular track there. On the semicircular track, the wiper is going to move. It is a minute wiper or a miniature wiper. And the wiper can be moved by means of rotating a screw at the top by means of a screwdriver. So this is called as a small potentiometer or preset. And you have other resistors and capacitors. So what is the circuit now? This is again an oscillator circuit. But you are seeing an op-amp now. So this is basically a Wien bridge oscillator circuit which I am going to show you now. It is a Wien bridge oscillator circuit. We have seen the regular phase shift oscillator using op-amp, using FET, using BJT. Now let us see a slight variation of the same phase shift oscillator circuit using another variation called Wien bridge oscillator. Now this is the standard oscillator circuit used for general applications in the range of 5 Hz till 1 MHz. You already have the formula 1 over 2 pi RC into root 6. Now as we know, when we use op-amp, we don't have to worry about the input impedance factors where we had it in BJT. Now in the op-amp we can have a gain setting RF and RI. Now you can see that there are 2 capacitors and 2 resistors. Then you have a preset and you have an additional resistor. You will have to visualize the operational amplifier. Operational amplifier will have RF and RI. Then right now we are seeing only 2 capacitors and 2 resistors, which means what? Instead of 3 capacitors and 3 resistors, we are having 2 capacitors and 2 resistors. Now that is the change that is happening here in this oscillator circuit, where by means of some peculiar arrangement, we will get 180 degree phase shift by means of lesser number of components. That is what a scientist called Wien did it. That is why it is called as Wien bridge oscillator. Now this is the standard oscillator which is used in many applications. I have been telling you about sirens and I have been telling you about beepers, and in most of such things Wien bridge oscillator can be used. Right from 5 Hz till 1 MHz we can use this. It uses the lead lag circuit as the resonant feedback, which means we had earlier seen only the lag circuit, CR, CR, CR. We had used the lag circuit there. We did not use the lead circuit. Now we can combine a lead circuit as well as lag circuit to get 180 degree phase shift. Now the series capacitor blocks low frequencies, parallel capacitor bypasses high frequencies, and hence the phase angle varies between plus 90 degree till minus 90 degree. Unlike in the earlier case, we used to have phase shift between 0 to 90 degree. Now in this case, we will have phase difference between plus 90 degree till minus 90 degree. That is actually 180 degree itself. So using 2 circuits instead of 3 which we used in the earlier cases, using only 2, but one is a lead circuit, one is a lag circuit. Using both, we can obtain 180 degree phase shift. So the output remains maximum in the mid range at the resonant frequency where the phase angle is 0 degree now, because it is going from plus 90 degree till minus 90 degree. Now you don't get confused by when I say that the phase angle is 0 degree, because the Bar-Khausen criterion says that even the feedback network should produce 180 degree phase shift. That is going to be produced here also. With additional components, with the op-amp, the total loop is going to produce 360 degree phase shift. That is going to happen here also now. But when I mention here as where the phase angle is 0 degree, that is with reference to the lead lag circuit. That is plus 90 to minus 90 when it is happening. The mid range is there 0 degree. So output remains maximum in the mid range. That is the resonant frequency. Now this is that circuit where one CR and one RC together they are there. You can see this R corresponds to this C and this C corresponds to this R. Now both are having the same value. C will have the same value, R will have the same value. Now when we combine lead and lag like this, let me annotate. This C and this R is a lag circuit, whereas this R along with this C is a lead circuit. Now there is a combination of lead as well as lag circuit. So unlike the earlier circuits, here we don't have 6 components, we have only 4 components. That means we are saving the number of components. That is the advantage of Wien bridge oscillator. Now beta in this case, when we apply our mathematical analysis, beta in this case will be 1 over square root of 9 minus xc by r minus r by xc whole squared. And the angle which we get is tan inverse of xc by r minus r by xc divided by 3. Now you don't have to remember this complicated formulae. We are not going to use this formula as such. Okay. I am showing you only for you to understand, that's all. You don't have to remember the complicated formulas. You have to only remember the final equation for the output frequency. In all these oscillators, you will have to remember the equation for the output frequency. When R equals Xc, resonance occurs. You can see here, we have Xc by R, R by X. When the resistance equals the reactance of the capacitance, that is when the resonance occurs. And when the resonance occurs, the feedback factor is 1 by 3. So it will be, you can see here, it will be square root of 9, it will be 3 because these two get cancelled. So the feedback factor beta is going to be 1 by 3. Now whenever there is beta 1 by 3, you can see there is a resonance occurring. When the resonance is occurring, there will be a 180 degree phase shift by this particular circuit. And that is when the circuit will start oscillating. You can see at the right side picture where at the resonant frequency, the phase angle is 0 degree with respect to this lead and lag. Otherwise, it is in between plus 90 degree till minus 90 degree. So the formula for this Wien bridge oscillator is Fr equals 1 by 2 pi Rc. That's all. There is no root 6 here. You understand? In the case of our conventional RC phase shift oscillator, it was 1 over 2 pi root 6. And in the case of BJT oscillator, it was 1 over 2 pi RC into root 6 plus 4 into RC by R. But in the case of a Wien bridge oscillator, it is only 1 by 2 pi RC. That root 6 term is missing here because the feedback circuit is different in this case now. So this is a Wien bridge oscillator circuit using op-amp. You can see an op-amp here and you can see one R and one C, one more R, one more C. So this complete circuit is now the feedback circuit and the upper circuit is now the op-amp. Now what may be the use of a tungsten lamp? I'll tell you later about the usage of tungsten lamp. But you know that for the operational amplifier, we have this gain setting resistors, right? When we have these gain setting resistors, earlier in the earlier circuits, we had some requirement on the value of A. Okay. Now in this case, we have no such requirement of value of A. Actually, we can have a gain also along with the oscillation. That's why you can see 2R dash by R dash is there, which means this op amp can be used to produce 2 times the voltage gain. AV in this case will be 2, because you already know for non-inverting, for the inverting configuration of the op amp, voltage gain is given by minus of RF by RI. Here RF is 2R dash, RI is R dash, is the tungsten lamp. So because of this, the amplifier is utilized to give the gain of 2, and the feedback factor is going to produce 180 degree phase shift. Okay. Now this is a Wein bridge oscillator. Of course, you need not write the tungsten lamp always. You can simply write RF and RI also. It is not necessary that you will have to use a tungsten lamp. Why I am showing you tungsten lamp is, this is discussed in the textbook Malvino, where he discusses about the stability of the oscillator using a tungsten lamp, which was an earlier measure used by the designers. So I thought, along with them some historical input, Malvino discusses all these points. So I thought, let me put that point here also. Otherwise, you can simply write here RF, you can simply write here as RI, feedback resistance and input resistance. No need of connecting a lamp to the oscillator circuit. Now let me proceed with the next slide, where I have discussed these things about the tungsten lamp. Now this Wein bridge oscillator circuit uses both feedback types, positive feedback through the lead lag circuit and negative feedback through the voltage divider circuit. You can see here, the voltage divider circuit is going to give the negative feedback, and the lead lag circuit is going to give the positive feedback. So using the negative feedback, we have seen earlier that even the negative feedback has got 6 advantages. That was in the case of the amplifiers. But now this is an oscillator. Still, those advantages of negative feedback to some extent are obtained even in this circuit. It has both feedbacks. Anyhow, it has to be a negative feedback, right? Because amplifier has to produce 180 degree phase shift here. Operational amplifier, when it is used in the inverting configuration, that is negative feedback itself. So it is necessary here. So this circuit uses both feedback types. At power up, there is more positive feedback, and A beta will be greater than 1, and hence oscillations will build up. You already know that we have to maintain a factor of A beta should be equal to 1. Now when this circuit switches on, there will be more of positive feedback, because the transistor would not have been stabilized, or the op amp would not have been fully stabilized. You will learn more about stability analysis in the next semester in a course called control systems, where this term A by 1 plus A beta is going to come again in the next semester. So what I am telling is, as soon as you switch on this particular Wein bridge oscillator, because we have an op amp is containing many transistors inside. So immediately the operational amplifier will not attain a stability there. It will take some time. So until then, there will be more positive feedback. You can see here in the circuit. Until this op amp stabilizes, there is this positive feedback. But oscillations are building up. But the op amp would not have got stabilized with the gain. That is where tungsten lamp helps. So slowly when the tungsten lamp heats up, its resistance increases. At power up, there is more positive feedback, and A beta is greater than 1, hence oscillations build up. Slowly when the tungsten lamp heats up, its resistance increases. And when it equals R dash, tungsten lamp is going to have a negative temperature coefficient. Means when the temperature increases, it's a positive temperature coefficient. When the temperature increases, resistance increases. The lamp's filament is going to have a positive temperature coefficient. So when the tungsten lamp heats up, its resistance increases, and when it equals R dash, what happens? Feedback resistance is 2R dash. When it equals R dash, there is a gain factor of 2. So when it equals R dash, voltage gain in closed loop is 2R dash divided by R dash plus 1 equals 3. Why this 2R dash by R dash plus 1? Now because of the positive feedback. It is working like a inverting amplifier also on the other side and non-inverting amplifier also on the upper pin. Please recall the circuit. I am going to show you again. See, you have this positive feedback. Can we say it exactly as a negative feedback? Negative feedback is also there. Positive feedback is also there. Now, should we consider it as a inverting amplifier? Should we consider it as a non-inverting amplifier? Now, when the feedback is coming here, it is basically now working like a non-inverting amplifier. Okay. So, when it is working like a non-inverting amplifier, the gain is 1 plus RF by RI. That is the point here. So when the gain is 1 plus RF by RI, RF is 2R dash, RI is R dash. So it is now 3. Total closed loop gain will be 3. And AVCL into beta. We already know that beta is actually 1 by 3. We have seen earlier how beta is going to be 1 by 3. So 3 into 1 by 3 is going to become 1. That way A beta is going to become unity. Now that is achieved by means of the tungsten lamp. If the tungsten lamp is not there also, the circuit is going to work. Okay. It is not that only when we connect the tungsten lamp and that is when it becomes A beta equals 1, then the circuit will work. It is not so. Without which also Wien bridge oscillator is going to work. But at that time we may use a preset. That is why in the breadboard I showed you there was a preset or a small potentiometer. Now, when we use a tungsten lamp, the advantage is that somehow system will stabilize by itself. And we don't have to have a fine tuning there. There is no manual work required in the case of the circuit shown here. Otherwise, if you have to replace the tungsten lamp, then we have to connect a separate small preset. Using that, we have to fine tune for getting the output. So at this point, the oscillations become stable and the output voltage will have a constant peak to peak value. And oscillator is ready to produce a smooth and a constant AC output. And we can use it for our applications such as sirens or beepers. This is about Wien bridge oscillator. Now you can see this circuit of Wien bridge oscillator. Why is it called as Wien bridge now? Do you see any bridge here? You can see RC, RC, one more R here. Actually, it is considered as a bridge configuration, just like a Wheatstone's bridge. See, you can see that this lead circuit and lag circuit are connected here together in the left side branch. And in the right side branch, you can see this R3 and R4. Now, R4 is connected to ground. R3 is connected back to output. That means this R3 is now the feedback resistor RF and R4 is the other resistor whichever I mentioned as RI, and you have the lead lag circuit here. Now basically this is a bridge circuit only. That is why it is called as Wien bridge oscillator. The same circuit is visualized in a different way now. Now the tungsten lamp corresponds to this R4. Okay. So now in this you have a formula F0 equals 1 over 2 pi into square root of R1 C1 R2 C2. R1 into C1 into R2 into C2, considering this lead lag circuit. Now performing the bridge analysis, we have R3 by R4 equals R1 by R2 plus C2 by C1. Performing the bridge analysis just like the Wheatstone's bridge analysis. So we have R3 by R4 equals R1 by R2 plus C2 by C1. If R1 is equal to R2 and if C1 is equal to C2, what is this formula is going to become? This formula is going to become F0 equals 1 over 2 pi RC, because it is square root of R square into C square. When R1 is equal to R2, C1 is equal to C2, The formula is going to become 1 over 2 pi RC. Now through the bridge analysis, when R3 by R4 is equal to R1 by R2 plus C2 by C1, when R1 is equal to R2 and C1 is equal to C2, then R3 by R4 is going to be 2. That is what is shown there as 2R dash and R dash. Okay. So in this way, we can have a VN bridge oscillator circuit. I will end today's class with this slide. I hope you have understood the functioning of the VN bridge oscillator. In the next class, we will cover the other oscillator circuits. Now for the time being, it is already time up now. I am going to close the class now. See you in the next class. Okay. So the WebEx is showing still there are 5 minutes. So let me slightly continue. Let me see what is there in my next slide. Yeah, in my next slide, I have an exercise for the VN bridge oscillator only. So let me complete this exercise. It's a very simple exercise. Again, you can see 2 happy kids are exercising. Obtain the RC values for a VN bridge oscillator with an output frequency of 20 kilohertz. Now you know the formula. F naught equals 1 over 2 pi RC. F naught is given 20 kilohertz. Now, I am not telling you to solve this because you will have to assume one of the unknowns. You will have to assume R, then you will get C. So, let me proceed. Let R be is equal to 100 kilo ohms. When let R is equal to 100 kilo ohms, then we get C is equal to 1 over 2 into pi into R into F. We get the capacitance value as 79.62 picofarad. So we got R, we got C. Now, if R4 is 100 kilo ohms, then R3 has to be greater than or equal to